Hello students, now let us start the first chapter of class 12 and that is relations and functions. Here you can clearly see that this chapter is important both for boards as well as competitive exams. Before we get into the chapter, let us revise what we have already studied in class 11, that is what is a Cartesian product, what is a relation, okay? For that, let us take two sets, set A and set B. Let us take some elements in set A as sea turtle, eagle and lion. Let us take some elements in set B as shark, whale and deer. Now, before we discuss what is a Cartesian product, let us understand one small thing, and that is every mapping can be represented as an ordered pair, something like this. Let us say mapping is from sea turtle to shark. Now, this can be represented as an ordered pair, something like this. Sea turtle, comma, shark. Sea turtle is being mapped to shark. So, therefore, first sea turtle will come, next shark will come. Just put them in brackets. This ordered pair represents this mapping. Okay. Now, let us say, for example, shark is being mapped to sea turtle. Then how do you write this as an ordered pair? Very simple. First shark will come, next sea turtle will come, and just put this as an ordered pair. Okay. Next, Cartesian product is every way of mapping from one set to the other set. Let us take every way of mapping from set A to set B. Okay. So, what is the meaning of every way of mapping from set A to set B? Means every element of A is mapped to every element of B. Okay. So, by doing which sea turtle should be mapped to all the elements of B, eagle should be mapped to all the elements of B, and lion should be mapped to all the elements of B. Now, corresponding to each mapping that is there here, there will be an ordered pair. So, therefore, corresponding to all of these mappings, these are the ordered pairs. Now, if you write all of these ordered pairs in one set, that is called A cross B, because we are mapping from A to B, every element of A to every element of B. So, therefore, you write A cross B. Let us say, for example, if you need to write B cross A, then how do you write it? Very simple. Just map every element of B to every element of A. So, all of these mappings, when written as ordered pairs, enclosed in brackets, this represents a set and this is B cross A. Now, let us discuss what is a relation. In Cartesian product, we have taken all ways of mapping from one set to the other set, isn't it? Right? But in relation, you will take only those mappings which satisfy a specific condition. That is the only difference. Okay? Let us understand this through some examples. Say R1 is a relation which is mapped from A to B. And the condition here is A eats B. Only then the mapping has to be done. Now, what is A here? A is any element of set A and B is any element of set B. So, therefore, any element of set A is mapped to any element of set B under the relation R1 only if element of set A eats element of set B. Now, mathematically, the same information about R1 can be written like this. R1 is a relation defined from A to B such that A R1B if A eats B. A is an element mapped to B under the relation R1 if the condition. What is the condition? First element should eat the second element. Okay. So, now let us take this set diagram. In this set diagram, element of A is mapped to element of B only if element of A eats element of B. So, does sea turtle eat any element of set B? No. So, therefore, there won't be any mapping out of sea turtle. In the same way, eagle does not eat any element of set B. So, therefore, there won't be any mapping out of eagle. And lion does not eat shark, lion does not eat whale, but lion eats deer. So therefore, lion to deer. Mapping will be there, and corresponding to this mapping, there will be an ordered pair. So therefore, lion comma deer is the ordered pair, and this, if you are putting in a set, then that set is R1. Okay. Now let us take the next example. In this example, R2 is a relation which is mapped from A to B, and the condition is A is eaten by B. So if A is an element which is eaten by element B, then A is mapped to B. Okay. So mathematically, how do you write this? Very simple. R2 is a relation defined from A to B such that A are to B if A is eaten by B. So now let us take this set diagram. So set A element is mapped to set B element if set A element is eaten by set B element. So now, is sea turtle eaten by shark? Yes. So therefore, sea turtle will be mapped to shark. In the same way, is sea turtle eaten by whale? Yes. So therefore, sea turtle is mapped to whale. Sea turtle is not eaten by deer. So therefore, there won't be any mapping from sea turtle to deer. Similarly, eagle is not eaten by any element of set B. No problem. Let us go to the next element, and that is lion. Lion is also not eaten by any element of set B. So therefore, under the relation R2, we have only these mappings, and these mappings, just write them as ordered pairs, put them in a set, and this set is R2. Now let us take the next example. In this example, R3 is a relation which is mapping from A to B, and the condition is A and B are creatures. So therefore, element A is mapped to element B if both are creatures. That's all. So mathematically, how do you write this relation? Very simple. R3 is a relation defined from A to B such that A R3B if A and B are creatures. Now let us take back the set diagram. R3 is a relation which is mapping from set A to set B. Sea turtle, is it a creature? Yes. Sea turtle can be mapped to all the elements of set B because all of them are creatures. So sea turtle is mapped to all three. Eagle is mapped to all three, and lion is also mapped to all three because all of them are creatures. So therefore, all of these ordered pairs, just write them in a set, and this is R3. In this condition of R3, we got all ways of mapping from A to B. No problem. If you get no mapping or all mappings, that is not a problem. Here, every way of mapping from A to B is R3 in this case because of the condition. So therefore, here R3 happens to be A cross B. So now let us take mathematical examples to understand relation. Till now we have taken a very general example, but of course we have covered all the points that are needed to understand what is a relation, right? So now let us take more relevant examples. A mathematical example. Let us take a set A containing elements 1, 2 and 3. Relations are defined on A. Okay. Now till now we have seen relations defined from A to B, isn't it? So here, if you just now we have done from A to B. That is how we are defining our relation. So therefore, our relations were subset of, okay, A cross B. Our relations were subset of A cross B. But if you are defining relations on A, means what? For relation, you need two sets. Before we had two clear sets, A, B, from A to B. So therefore, A cross B. Relation is a subset of A cross B. If you are defining relation on A, there is only one single set that is given. So therefore, you have no other go. The second set also should be the same set. So therefore, in that case, relation will be subset of A cross A. That's all, right? You are given one single set. So therefore, you are using the same set on both the sides. So therefore, our relation will be subset of A cross A if you are defining the relation on A. Okay, so therefore here we are defining relation on A, And these type of relations is what we are going to see throughout the class 12 part of relations. Okay, so whatever you are going to study in class 12 part of relations, all of the places you will have relations which are defined on one single set. Relation, if it is defined on A, means our relation is subset of A cross A. If relation is defined on B set, then our relation is subset of B cross B. That's all. Okay, fine. So everything else is the same. Here also, if you have a relation which is defined on A, again you will have one condition. Based on that condition, you will take those ordered pairs from the Cartesian product into your relation. Same thing, everything is the same, just you are defining on one single set. That's all. Okay, these are the relations which we are going to, basically, study upon in class 12. Okay, we are going to discuss different types of relations that will be defined on one single set. That we will see little later. Okay. So now we are taking a mathematical example to understand the relation, and we are defining relation on one single set. So therefore, relation is a subset of Cartesian product. Here it will be A cross A. Now, one thing which I want to tell you is in NCERT, in class 11, clearly they have mentioned that this symbol is for subset. This symbol is for subset. Okay. But in general, means if you are not taking the NCERT book, but any other book, then the subset symbol will be like this. Subset symbol will be like this. And if you are writing like this, that means this is a proper subset. Proper subset. So now, I will be using this symbol itself for NCERT or for the board's purpose, because, that is how it is mentioned in NCERT. Okay. But in some IITG videos of the same chapter, you will find something like this, and this means subset. Okay, when you write like this, it means subset. When you write like this, it means proper subset. Okay, what is a proper subset and what is a subset? The reason I am explaining is just before I have written R is a subset of A cross A. Now, actually I should read it as R is a proper subset of A cross A, but not according to NCERT. According to NCERT, this is R is a subset of A cross A. What is a proper subset? That we will study, or I will be discussing in onto functions J video. Okay, there I will be discussing what is a subset and what is a proper subset. The difference, if you want, you can go and see the initial part of the video. But now let us not get into what is a subset, what is a proper subset. That is a different discussion. Okay, so this is the symbol for subset. I hope it is clear now. So now a relation is defined on A, and our relation R1 is containing ordered pairs x comma y such that x is coming from set A, y is coming from set A, and 4x minus y is equal to 0. Okay, so here we have a relation where we are specifically mentioning the condition. Okay, what is the condition? 4 times the x coordinate should be equal to y coordinate. 4x minus y is equal to 0 implies 4x is equal to y. So that is the relation between x and y. Where is x coming from? Set A. Where is y coming from? Set A. As usual, right? Any ordered pair in the relation should come from A cross A only, right? So therefore, if you are taking an ordered pair which is coming from A cross A, then what does A cross A contain? Ordered pairs. Of these ordered pairs, you are taking, some ordered pairs in our relation. So therefore, this ordered pair is coming from here. So in any Cartesian product, this one, in every ordered pair, the first coordinate will come from this set, the second coordinate will come from this set. So therefore, this should come from set A and this also should come from set A. That's all, right? Okay. So all of this are already known. Now let us get into writing the same set. We are writing R1 itself in a different form. Okay. Now let us write ordered pairs here. Here we have mentioned like a condition. Okay. So this is, if you remember in class 11, there is something called as set builder form. Set builder way of writing a set. Set builder form. What is a set builder form? If you remember, you have studied something like this. A is a set which is containing elements such that x belongs to natural numbers and x is less than or equal to 5. So this is set builder way of writing a set, where you are telling the elements of this set are x, and what is this x? X is a natural number and x is less than or equal to 5. This is set builder way of writing a set. Okay, what is the roster way of writing a set? This is R-O-A-S-T-E-R, roster form. Roster form of writing a set, you directly give the elements. Instead of giving the property, you will directly give the elements. Okay, so for this set, what are the elements? So here x should be a natural number and x is less than or equal to 5. Natural numbers are 1, 2, 3, 4, 5, 6, so on like this. So therefore, it should be a natural number and less than or equal to 5. So therefore, 2, 3, 4, 5. So we are writing the same set in roster form. The same thing we are doing here also. Here R1 is given as set builder form. This is set builder form because you are giving the property. If you are writing in roster form, then it is very easy. X is coming from set A and Y is also coming from set A. And what should be the condition? Condition is Y should be 4 times x. Okay. So therefore, if Y is equal to 4 times x, then take x is equal to 1. Y should be equal to 4. 4 is not possible here. Let me show you the set diagram. Here there will not be any ordered pairs that are possible. 1, 2 and 3. Now if you are doing the mapping, then y is equal to 4 times x. Okay. What can x take? X can take only those values that are there in set A, right? Okay. So therefore, if x is equal to 1, y should be equal to 4. Is it there? No. So leave it. If x is equal to 2, y should be equal to 8. Is it there? No. So therefore, leave it. If x is equal to 3, y should be equal to 12. That is also not there. Leave it. So therefore, here for this condition, we cannot take any ordered pair from A cross A. Isn't it? Right? For this condition which we have here, we cannot take any ordered pair from A cross A. We have tried one by one. With 1 we have seen. Can I take with 1? No. So therefore leave it. Can I take with 2? For x is equal to 2, y should be equal to 8. So I cannot take it. So therefore leave it. Means leave it means leave this element. Next go to the next element. With this also I am not able to pair anything. Okay. So therefore here we have a null set. Okay. So this is roster way of writing the same set. Instead of giving the condition, you are clearly writing whatever are the ordered pairs that are going to come, or whatever are the elements that are there in that set. Here there is no element, so therefore you are writing null set. Okay. So we have written what is this relation R1. Okay. So next let us come to relation R2. This is also defined on A. Now here the condition is x is equal to 2y. So x coordinate should be twice of the y coordinate. Okay. So for clarity purpose, we can draw this diagram. Okay. So this is R2, 1, 2, 3, 1, 2 and 3. Now x should be equal to 2 times y. Okay. So if what can be y? Y can be 1 or 2 or 3. Okay. So if y is equal to 1, then what is x? X is equal to 2. Okay. So if y is equal to 1, x will be equal to 2. Okay. You can see from x side also, nothing wrong. We'll do like that also. Okay. First, y should be, let us do it from y side. If y is equal to 1, x should be equal to 2. Mapping is done. If y is equal to 2, x should be equal to 4. Is it there? No. Leave it. Next, for y is equal to 3, x should be equal to 6. That is also not possible. So therefore, the only ordered pair that is possible is 2, 1. Okay, fine. Now, if you want to do, you can do the same thing from x side also. Let us do it from x side. Okay, what can x be? 1, 2, 3. Okay. So if x is 1, what should be y? Y should be equal to 1 by 2. So just before we have seen, for x is equal to 1, is y equal to half possible? Y can be 1 or 2 or 3. Okay. So y is equal to half is not possible. So with x is equal to 1, you are not getting any ordered pair. Next, with x is equal to 2, you will have y is equal to 1. So is y equal to 1 possible? Yes. So therefore map 2 to 1 just before we have done. And you can check it for yourself. If you put 3, then y will be 3 by 2. That is not possible. So therefore we didn't do any mapping. Simple. So therefore we have written R2 also in roster form, and that is 2, 1. Got it? Simple. Okay. So this is how we are writing relations in a mathematical example. Everything is the same. Just the set has changed. The condition has changed. That's all. Right? Okay. So now let us go to the next slide. Note. Let us write some note points. Relation from A to B means relation is defined on A cross B. Our relation will be subset of A cross B. Whereas if relation is defined on A means our relation is subset of A cross A. This we have studied. Just we are writing as a note point so that we will not forget. Next, example 1. What was example 1? R1 is equal to ordered pairs x, y such that x belongs to A, y belongs to A, and x minus 4x minus y is equal to 0. This was example 1. This can also be written as, this we have seen in the general example also. Just before this mathematical example, also we have seen a relation can be written like this. What is that? You are mapping from x to y under the relation R1. Now you write the condition. So to write the condition, you have, this way also. Means before, if you remember, we have written like this. A, R1, B, if A eats B. Correct? So A is an element mapped to B under the relation R1 if A eats B. Here also it is the same thing. X is an element which is mapped to Y under the relation R1 if you write the condition, or you write like this also. If and only if 4x minus y is equal to 0. There is no difference between this way of writing and that way of writing. You are communicating the same information, x r1y, if 4x minus y is equal to 0. Is there any difference between this one and this one? Both are saying the same thing. X should be mapped to y under the relation R1 if 4x minus y is equal to 0. That is this. That is what this is saying. Here also it is the same thing. If and only if this is happening. So therefore, you can write like this, you can write like this, or you can write it little differently also. Something like this. If x r1y, then 4x minus y is equal to 0. So these are just different ways of writing a relation. Okay. So that is what we are studying here. Because in some problems it will be given here. It will be given like this. Okay. So you are very clear. We are talking about a relation R1 and this is the condition. Okay. So we are talking about relation R2 and this is the condition. So you can write, means you can talk about a relation like this or like this or like this also. Okay. Fine. Fine. So therefore these are different ways of writing a relation. So therefore we have understood what is a relation, right? How is relation subset of Cartesian product? What is the meaning of relation defined from A to B? Means relation is subset of A cross B. Next, what is the meaning of relation defined on A? Means our relation is a subset of A cross A. Next, these are different ways of writing a relation, right? So this much is more than sufficient. Let us go into the class 12 part of relations. Okay, that is types of relations. So let us get into that. Okay. Okay, so now let us take different types of relations. Okay. So on what basis are you going to divide the relations, or on what basis are you going to decide if this relation is of this type or not? There will be some specific property, and based on that property, you will say if that relation is this type or not. Okay, so let us discuss one by one. You will be very clear with them. Now, first one is empty relation. The name itself is saying empty relation, means this relation does not have any ordered pairs in it. So therefore, you are giving a specific name to it, and that is called empty relation. Okay, so just before we have seen a relation something like this. We had relation R1, which is having ordered pairs x, y, such that x is belonging to A, y is belonging to A, and 4x minus y is equal to 0. So this is an example of an empty relation. Because when we are writing the ordered pairs, we are getting null set. Clear? Okay. So this relation, because it does not have any ordered pairs, you are giving a specific name to it. Okay. So as I told you, if a relation is following a specific property, then you will give a specific name to it. So here, what is the property? This relation should not have any ordered pairs. Okay. So a relation R in set A is called empty relation if no element of A is mapped to any element of A under this relation. Okay, fine. So just before we have seen, we had taken 4x minus y is equal to 0, because of which there was no mapping that is happening under the relation R1. 1, 2 and 3, 1, 2 and 3. So this we have seen just before, right? So this is the condition. So if no element of A is mapped to any element of A, that means there are no ordered pairs. The meaning of this is related to any element of A, means our relation has no ordered pairs. So that is R is equal to null set. So obviously every relation is a subset of Cartesian product. Okay. So here we are defining on A. Okay. As I told you, all the relations that we are going to discuss in class 12 will be defined on one single set. Okay. So here it is defined on A. So therefore our relation will be a subset of A cross A. So here it is null set. Null set is also a subset of A cross A, right? Null set is a subset of every set. Okay. So therefore we have understood what is empty relation. Let us take one example here so that it will be very clear. Let A be a set which is having 1, 2, 3, 4. A relation R is defined on A such that R is a set which is a relation which is having ordered pairs x comma y. X should come from set A, y should come from set A, and x plus y should be greater than 9. So this is the condition or rule. So based on this rule, you have to do the mapping. So R is relation which is defined on A means our relation is a subset of A cross A, right? Okay. So this you can do it in rough if you want, but if it is not needed, then you can skip it as well, because even the boards do not ask for this mapping diagram. Okay. So here we are writing the same relation in roster form. So here what are all the ordered pairs that can come? X plus y should be greater than 9. Now you see, if you take 1, you map it to 1. 1 plus 1 is 2. 2 is greater than 9 or less than 9? 2 is less than 9, means 2 is greater than 9 is not happening. So therefore I cannot map 1 to 1. In the same way I cannot map 1 to 2, 1 to 3, 1 to 4 also. In all of these cases, the sum is not greater than 9. In the same way, you can check it with 2, means the highest sum will come because of mapping 4 to 4. That itself is 8. So any other mapping will anyway be less than 8 itself, because 4 to 4 is 8 and any other mapping is less than 8. So therefore, our relation will not have any ordered pairs. It will be a null set. Implies R is an empty relation. Okay. So therefore, we have understood that R is an empty relation. Okay. So now let us take the next type of relation, and that is universal relation. This is exact opposite to empty relation. In the name itself, it is their universal relation, means it will have all the ordered pairs possible. Obviously, because relation should be a subset of Cartesian product, here all relations we are defining on one single set. So therefore, means R can contain all the ordered pairs, means obviously it cannot contain any different ordered pairs. It can contain all the ordered pairs which are there in A cross A only, because R should be subset of A cross A. So therefore, if you get R is equal to A cross A, then that relation you are giving a name, and that is universal relation. Okay. So let us read the definition. A relation R in set A is called universal relation if each element of A is mapped to every element of A. Means R is equal to A cross A. Let us take an example. So let A is equal to 1, 2, 3, 4. Let R be defined on A such that X R Y implies X plus Y is less than or equal to 8. So before we get into this one, we have taken one example just before, like in the general example, we have said that A R3B if A and B are creatures. So therefore, here in this relation R3, we got this is equal to A cross B there, right? Okay. So the same type of thing we are discussing here. But always remember, the naming is given when the relation is defined on one single set. Okay. That is when you are giving the naming. Whatever it is, if it is empty relation or universal relation or the next relations that we are going to study, always you are going to give the name when it is defined on one single set. For defining on different sets, there is no naming that is given. Okay, even if it is like this. This is an example of universal relation because R3 is equal to A cross B. But that is not the way the naming is being given by convention. Okay, so it is being done only when the relation is defined on one single set. Okay, so therefore here x plus y should be less than or equal to 8. Same mapping diagram, same set, right? So A to A, and just the condition is different, that's all. So 1, 2, 3 and 4, 1, 2, 3 and 4. Mapping is done under the relation R if x plus y is less than or equal to 8. Before, for universal relation, x plus y is greater than 9. So just a difference in the condition, because of which our ordered pairs also will change accordingly. So x plus y should be less than or equal to 8. So therefore, I can map 1 to 2, 1 to 3, 1 to 4 and so on like this. You can map 2 to all of the elements of A, 3 to all of the elements of A, 4 to all of the elements of A. So in all of them, the sum will be less than or equal to 8. So therefore, here you will have R is equal to the ordered pairs 1, 2, 1, 3, 1, 4, and in the same way 2, 1, 2, 2, 2, 3, 2, 4, and 3, 1, 3, 2, all of that. Okay, so instead of, how to write it, so let me just, this is what will come here, 4, 1 to 4, 4. So these are the ordered pairs. So clearly we can see R is equal to A cross A. So if R is equal to A cross A, then you are giving a specific name to this, implies R is a universal relation. R is a universal relation. Okay, fine. So now let us take the next example. Now we have a NCERT example here, which is directly from the textbook. Let A be the set of all students of a boys' school. Okay, show that a relation R in A given by R is equal to A comma B if A is a sister of B is an empty relation, and R dash is equal to set containing ordered pairs A comma B. The difference between the heights of A and B is less than 3 meters. Is a universal relation. So here, if you see, there are two questions here. That is, first of all, means this is still here, it is the first part of the question, and after that, it is the second part of the question. So first we have to prove R is an empty relation. Okay, and this relation is defined on which set? Let A be the set of all students of a boys' school. Okay, so you have a set which is having all students of a boys' school. Next, show that the relation R is an empty relation, and the condition in this relation is A is a sister of B. Now, how is it possible? You are saying you are defining your relation on set A. On set A means all the students here given are boys. So the mapping can be done if A is a sister of B. So how can you find sister? Means all are boys, right? So how can you find sister of some element, right? So therefore, R will be an empty relation. Next, R dash, that is also very easy. The difference between the heights should be less than 3 meters. So it will anyway be less than 3 meters. See, 1 meter is approximately equal to 3 feet and 3 inches. Okay. So 3 meters means that is very easy, 9 feet, 9 inches. So the difference between two heights of any humans will be less than 9 feet 9 inches, isn't it? So therefore, this will be a universal relation. So that's all. So let us write this same thing, as in the boards format. So let A be the no element of A can be sister of any element as A contains, A, capital A means it is set A. So capital A contains only boys, implies R is equal to null set, implies R is a empty relation. Empty relation. Okay, so that's it. So we have shown that R is an empty relation. First part is completed. Let us come to the next one, and that is we have to show R dash is a universal relation. So therefore we have to show R dash is equal to A cross A. And just before we have seen, that is also very easy. Difference between heights of any two students, okay, or any two humans for that matter, but here there are students, so let us write students. Any two students will certainly be less than three meters. Therefore, R dash will have all the ordered pairs in A cross A. Implies R dash is equal to A cross A. Therefore, R dash is a universal relation. Universal relation. Okay, so this is how we have shown that R dash is a universal relation. Okay, so now let us take the next part, and that is understanding reflexive relation. So in reflexive relation also there will be one property, and if the relation is following that property, you will give a name to it, reflexive relation. Now what is reflexive relation? In the name itself it is a reflection, right? So therefore, if you are taking, let us say, the same set as we have discussed just before, so always we are giving naming when mapping is done from set A to set A, okay, on the same set. Now when you say reflection, let us say for example this is our mirror. Okay, so means when one stands in front of the mirror, it will see one only. So therefore 1 should be mapped to 1, 2 should be mapped to 2, 3 should be mapped to 3, 4 should be mapped to 4. These ordered pairs should certainly be there, means every element and its reflection, that will be the same element. So that mapping should be there. There can be extra mappings, that is not what we are concerned about, but these should be there. Okay, when you will clearly understand when we do the problems as well. First let us take the definition. So basically a relation R in set A is called reflexive if A comma A belongs to R for all A belonging to A. Very simple. So for every element belonging to the set on which the relation is defined, okay, R is defined on A, for every element in this set, it should be mapped to the same element. So therefore A comma A should belong to R. Got it? Okay, so that is all. That it is very easy to remember as well. A comma A should belong to R for every element which is belonging to the set on which we are defining the relation. That's all. Same thing as we have seen before, 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, all of them should be there. So let us go to the example and let us understand if this means we have to see if each of these relation is reflexive or not reflexive. So here we have set A containing elements 1, 2 and 3, and all of these relations are defined on A. Okay, so here check if R1, R2, R3 are reflexive. All relations R1, R2, R3 are defined on A. Are defined on A. Okay, so therefore we are defining all our relations on A, and we have to see if this is reflexive or not. Okay. So because we are defining on A and A has 1, 2, 3, so I am sure you already understand that what ordered pairs should be there in our relation. Every element of A should be mapped to the same element. 1, 1, 2, 2, 3, 3 should be there. Only then you call it a reflexive relation, right? So therefore, 1, 1 is there, 2, 2 is there, 3, 3 is there. So therefore, implies R1 is reflexive. R1 is reflexive. Reflexive relation. Okay. So we understood R1 is reflexive relation. On what basis did we check? We have checked 1, 1 should be there, 2, 2 should be there, 3, 3 should be there. So put a tick mark on all of them. So here tick mark is not needed. In the next types of relations, I will show you how to do it with tick marks. It will be easy. We can do the problem without any error. Okay. So here it is not needed. We know very well what to check for. Okay. So here 1, 1 is there, 2, 2 is there, 3, 3 is not there. So therefore, this is not a reflexive relation. Implies R2 is not reflexive. Okay. Why is it not reflexive? Because as we have discussed before, every element of A should be mapped to the same element. Now 3 should be mapped to 3 means that ordered pair should be there. So the reason is as 3, 3 does not belong to our relation R2. Okay. So let us come to this one. We are checking the same things, 1, 1, 2, 2, 3, 3, all of them are there. Extra 1, 2 is there. That is not a problem at all. In the condition that we have taken in the definition, it is saying A should belong to R for every A belonging to A. If this is happening, then the condition is met and therefore this will be a reflexive relation. Okay, fine. So is the condition being met? Is our condition 1, 1, 2, 2, 3, 3 or A belonging to R, is it happening or not? Yes. So therefore, this is a reflexive relation. R3 is reflexive or reflexive relation. You can write relation also. So on the whole, I'm sure you would have understood. Every element of A should be mapped to the same element under the relation. And if that is happening, then it is reflexive. Extra is there, not a problem at all. Okay. But nothing should be missed from these. Okay. Let us go to the next one. Symmetric relation. Now, what is symmetric relation? In the name itself, it is there. Symmetric means if you have an ordered pair in your relation, then the reverse also should be there. That is what is symmetric. Simple. Okay. Let us say if 2, 1 is there in our relation, then 1, 2 also should be there. Means this should happen for all of the ordered pairs. Let us say 2, 1 is there and 2, 3 is also there. So 2, 1 is there. So 1, 2 also should be there. 2, 3 is there. And 3, 2 also should be there. If this is happening, then this type of property is happening for all of the ordered pairs. Then you call it as a symmetric relation. Simple. Okay. Let us see the same thing as a definition. If A1, A2 belongs to R, then A2, A1 should belong to R. That is the condition. Simple. Okay. So here don't get confused for all A1, A2 belonging to A. We will do the problem and then we will come back. Okay. Now A is a set on which we are defining our relations. So here also it is mentioned, means R1, R2, R3 are defined on set A. Okay. So we are defining all our relations on this set. Now we have to check if it is symmetric or not. Now we know what to check for. So therefore, let us do ordered pair by ordered pair. Here we will do using tick marks. 1, 2 is there. I am checking for this ordered pair. You are taking this ordered pair. So you have lifted this ordered pair, taken in your hand. 1, 2 is there. Is 2, 1 there? Yes. Put a tick mark on both of them. Okay. Completed? Fine. So now means there is nothing else to check. All the ordered pairs have tick marks. So therefore, implies R1 is symmetric. R1 is symmetric. When do you say? When all the tick marks are there on all of the ordered pairs. Okay. Next, come from here. Take the ordered pair 1, 2 in your hand. Okay. Is 2, 1 there? Yes. Put a tick mark on both of them. Okay. Next you take the next ordered pair in your hand. Okay, obviously you have put back the ordered pair which you have taken before. Now 1, 2 you have put it back, and 1, 3 you have taken. Is 3, 1 there? Yes. Put a tick mark on both of them. Next, all of them have tick marks. Next, come to 1, 1. 1, 1 is there. You have taken in your hand. So reverse is 1, 1. Is it there? Yes. So therefore, put a tick mark on this. So here, what did we understand? If you are taking an ordered pair, see if the other, means the flip one, is there or not. Put a tick mark on both of them. Once you have done that, now you came to 1, 1. The thing with 1, 1 is, if you reverse also, it is the same ordered pair. It is not a different ordered pair. No problem. Even if it is happening like that, means when you have both the coordinates same here, then when you reverse also, you'll get the same thing. Is that there? Yes. So therefore, you put a tick mark. So here you will put a tick mark only on that ordered pair. Simple, right? Here we were putting on both of them. Here we'll get a tick mark on one of them. So you got tick mark on all of them. Okay. So therefore, R2 is symmetric. Okay. Ordered pair by ordered pair checking and going forward. 1, 2 is there. Is 2, 1 there? No. So same thing. You have taken in your hand 1, 2. 2, 1 is it there? You are checking. No, you didn't get it. So therefore, instead of tick mark, you got cross mark here. Even if you get one cross mark, then that will not be a symmetric relation. Simple. Okay. So therefore, this is not a symmetric relation. R2 is not symmetric, or you can write symmetric relation. I hope it is clear now, right? So if you have an ordered pair in your relation, then its reverse should also be there. Even if it is not happening for at least one ordered pair, even then it is not a symmetric relation. So here 1, 1 is there, but its reverse, you have taken 1, 1, you do the reverse, it is 1, 1 only. Is it there? Yes. Put a tick mark. So tick mark is there on 1, 1. The problem is not with 1, 1 having tick mark. I told you all tick marks should come. Here it is not happening. So even if you find one cross mark, then that is not symmetric relation. Okay. The same thing in reflexive also. See, here we have seen 1, 1 is there, 2, 2 is there. Only 3, 3 is not there. Everything else is there. 1, 1 is there, 2, 2 is there. But even if you have at least one place where the rule is breaking, then it will not be that relation. Okay. So here it is not reflexive, and here it is not symmetric. I hope it is clear, right? Okay. So here for all A1, A2 belonging to A, if you have understood what is the method that we are following, that is more than sufficient. So what is being said here is this A1 and A2 should come from set A. That's all. Okay. So whatever are the ordered pairs that we are checking for, it should come from the given set, right? Okay. So that's all. So this is how you should check for if it is symmetric or not symmetric. The method should be clear. Okay. Next, what is a transitive relation? So in the name itself, it is there, transitive relation. Means very simple. Here transition is happening. So here, if A1, A2 belongs to R and A2, A3 belongs to R, then A1, A3 should belong to R. That is what this relation is saying. So very simple. If you have 1, 2, if you have 2, 3, then 1, 3 should be there, right? That is how you should check also. You will understand while we are checking. So now here we have to see if these relations are transitive or not transitive. So here let us write all of the relations, all relations R1, R2, R3 are defined on A. That is given in the question. So here the way you should check is also the same way as we have done the definition, and that is whenever you take an ordered pair, check for the second coordinate 2. Is there any other ordered pair starting with 2? Yes. So 2, 1 is there. 1, 1 should be there. Is it there? No. So therefore, this is not a transitive relation. R1 is not a transitive relation. Okay. Why is it not a transitive relation? Reason is 1, 2 belongs to R and 2 comma 1 belongs to R. Okay, this is R1. Okay, but 1 comma 1 does not belong to R1. Okay, clear? So that is what means you are checking the same rule just by ordered pair you are checking. That's all. Okay, so you got one cross mark here. So therefore no need of checking further. This is not what you are checking for. This is not transitive. Simple. Okay, let us come to the next one. So here 1 comma 2. I will take this ordered pair. Same method. The second coordinate is 2 here, isn't it? Right. So are there any other ordered pairs starting with 2? Yes. So 1 comma 2 is there, 2 comma 3 is there. 1 comma 3 is it there? Yes. Okay. Next, is there any other ordered pair starting with 2 other than this one? No. So therefore, for this checking is completed. Clear? Okay. So what you have done, you have taken this ordered pair. 2 is the second coordinate. Are there ordered pairs starting with 2? Yes. This with this you have checked. You know, the rule is not breaking. Are there any other ordered pairs starting with 2? No. So therefore, checking for this is completed. Next, come to the next ordered pair. 1 comma 3. You have taken this. Second coordinate is 3. So are there any ordered pairs starting with 3? No. So if there are no ordered pairs starting with 3, there is no need to check. Means there is no need to check further. You can put a tick mark. So I hope you are understanding. See, 2 comma 3 is there. Sorry, 1 comma 3 is there. And there is no other ordered pair starting with 3. So if it was starting with 3 and there was some coordinate here, then I will check for 1 comma this is there or not. Because this itself is not there, there is no checking needed. You can put a tick mark. Okay, the rule is not breaking. In the rule, it is clearly mentioned and. If this is there and this is there, then you should check for this. If this is there and this is not there, no need of checking. Put a tick mark. Simple. Okay, the rule is not breaking. Okay, so therefore, okay, so here 1 comma 3 we are checking. There is no ordered pair starting with 3. So therefore, no checking is needed. Put a tick mark. Okay, come to 2 comma 3. Same thing. So there is no other ordered pair starting with 3. So no checking is needed. Put a tick mark. 1 comma 1. Is there any ordered pair starting with 1? Okay, here. So you have taken 1 comma 1. Second coordinate is 1. With that 1 comma 2 is starting. So 1 comma 1 is there. 1 comma 2 is there. 1 comma 2 should be there. Is it there? Yes. Okay. So still the checking is not completed. You should check with all those ordered pairs which are starting with this one. Okay. So here 1 comma 2 is done. Is there any other ordered pair starting with 1? Yes. So 1 comma 1 is there. 1 comma 3 is there. 1 comma 3 should be there. It is there. So therefore, okay. Still any other ordered pair is starting with 1? No. So you have checked with all the ordered pairs starting with 1. Nowhere the rule is breaking. So put a tick mark. Because you got all the tick marks, implies R2 is transitive. Okay. R2 is transitive relation. So this is how you should check. Do it ordered pair by ordered pair. This is very simple. There is no complication at all. But students make some mistakes in these also. Because it is not because they don't know. Just, while checking, they do it little quickly and, they miss it. So that's why proceed with this method. Put tick marks and do it. You'll always come up with the right answer. Okay. Next, let us go to this one. 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4. We have to go ordered pair by ordered pair. I have taken 1 comma 1 into my hand. Second coordinate is 1. Is there any ordered pair starting with 1? No. So therefore, no checking is needed. Put a tick mark. Next, you take 2 comma 2. Okay, of course, you have put 1 comma 1 back. 2 comma 2. So second coordinate is 2. Is there any ordered pair starting with 2? Other than this one? No. So therefore, there is no checking needed. Put a tick mark. Okay. Next, is there any other ordered pair starting with 3? No. So therefore, put a tick mark. No checking is needed. Here also tick mark. So because you got all tick marks, implies R3 is a transitive relation. Is a transitive relation. Okay. I am sure you would have understood what is the rule. If 1 comma 1 is there and any other ordered pair is starting with 1, then only you should do the checking for 1 to this one. Here there is no other ordered pair starting with 1. So no checking is needed. Nowhere the rule has broken. Okay, fine. So that is how you have to check for if it is transitive or not transitive. Okay, so let us take the next type of relation, the last type of relation. So till now what we have discussed what is an empty relation, what is a universal relation, what is a reflexive relation, what is a symmetric relation, what is a transitive relation. 5 types of relations. This is the last one, and there is nothing to study here also. If a relation is reflexive, okay, you have checked for reflexive and that relation is reflexive. You have checked for symmetric and that same relation is symmetric also. For one relation, you checked for reflexive, it came out reflexive. You checked for symmetric, it came out symmetric. You checked for transitive, it came out transitive. So therefore, if a relation is all three, means it is reflexive, symmetric and transitive, then you are giving a special name to it. So what is that special name that you are giving to that relation? That is equivalence relation. If a relation is reflexive, symmetric and transitive, then you are giving a special category. This is equivalence relation. That's all. Okay, fine. So that is what is written here. So you have understood what is empty relation. No ordered pairs should be there in our relation. That is the first type of relation. Second one is this a universal relation? If it is a universal relation, the relation should have all the ordered pairs in the Cartesian product. So here it was R is equal to A cross A. This is the second type of relation. Third type of relation is it reflexive or not? How do you check for reflexive? A comma A should belong to R for all A belonging to the set. Means whatever are the elements that are there in our set, every element should be mapped to the same element. That is what this condition is saying. Next one is, what is symmetric relation? If A1 comma A2 belongs to R, if there is an ordered pair, then the reverse also should be there. That's all. Okay. So if that is happening, then it is symmetric relation. And what is a transitive relation? This we have seen just before. A1 comma A2 belongs to R, A2 comma A3 belongs to R. If these both are happening, A1 comma A2 belongs to R and A2 comma A3 belongs to R, then A1 comma A3 should belong to R. So that is a transitive relation. Okay, fine. So now let us do some problems, based on these. And the last relation is very simple. This is, you are not checking anything new here. You are checking for reflexive, symmetric and transitive. If the relation is all three, then you are giving a special name to it. Okay. So now let us do some problem solving on checking if it is reflexive, symmetric, transitive and equivalence relation or not. Okay.